Hey, good evening, everyone. So what we'll do is we'll be getting into double integrals and polar coordinates in a second. I want to do a few more problems from double integrals over general regions in 15.3. One of the things I've noticed is sometimes the students have a lot of questions about when you have to reverse the order of integration. So I just wanted to practice a couple things. We won't have to go solve an integral, but the idea that every one of these problems, I just want you, can you just reverse the order of integration of some setup? The whole purpose behind this is sometimes when you reverse the order of integration, the problem's a lot easier doing dx dy versus dy dx when you set up the double integrals. So, there you go. I'm going to function from 0 to 9. 0 square of x, function of x and y. And they wrote dy dx. Okay. Can you reverse the order of integration? Can you reverse the order of integration? We'll do a few of these. And once we're done with this, then we'll jump into the cool stuff, the polar coordinates. It's really neat. That's cool. But right now, just reverse the order of integration. So in the end, what's the easy stuff? You're going to have something like this. This is just going to turn into what? Dx dy. Do you have to reverse this? Remember, that represents the equation of the surface. Do you have to reverse this in any way, shape, or form? No. Whatever you see there stays. So if this said e to the x times y, I would write right here e to the x times y. If this said sine of x times y cubed, I'd write sine of xy. That does not reverse. So this stays. That stays. The only challenge is the what? It's this. And to do it, you really need to make a picture. That's the secret. Just draw a picture. So I'm going to draw a picture represent this. And this is where I write all over the place. So I'm thinking, okay, first of all, are these x's or y's? X's. So I'm like, okay, you're x's. Does everyone agree? I'm like, okay, those are x's. That means these are y equations. And if they're y equations, like y equals square root of x, y equals 0, I'm going to think this is the top and this is the bottom. And I'm going to think I got to shade between these two equations from x equals 0 all the way to x equals 9. I got a shade between those two regions. That would be the bounded region. I guess the only challenge is what's y equals square root of x look like? We really do need to get a sense of this image to see what it looks like. Y equals square root of x, just go like that? Yeah. Awesome. So I'm going to do that. And how far do I got to go? All the way out to 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'll stop there. Make a wall. Y equals square root of x. And y equals 0 is just right here, isn't it? So where are you shading? It's the key step. You're shading here. There you go. I'm not shading over here. I'm shading over here. All right. So far, so good? So now we're going to reverse it. You can do this by tilting your head and going like this. Who's my new top? And who's my new bottom? Right? And get everything in terms of x. These x equations. Or it's easier, we don't have to get the neck cramp like I was saying last class. We don't need to get a neck cramp. We can just think, who's my right hand side and who's my left hand side equations. So this will be your x equal to some right hand side. I'll put x above. And that curve right there is going to be your equation x equal to some left hand side equation. Well, let's start out. These have to be y values, and I have no idea what they are. So can you help me out? They have to be y values. The outer integral has to have values. What's that y value? 0. Y equals 0. What's that y value right there?
3.
3. Excellent. How'd you get that? Substitute the 9 into the square root of x, right? So if this was 8, square root of 8. right? But a square root of 9 is a nice, neat 3. So we had to do that. Now this isn't going to be top and bottom like I wrote before. This is going to be your right-hand side x equation. This will be your left-hand side. Who's the right-hand side?
9.
Good job. It's that wall right there. X equals 9. So this is just a 9. Who's your left-hand side? This is where I get this all the time on tests. I don't want to make, they think it's just 0. You go, no, it didn't go that far. What was the left? It was always getting bounded by this curve. And you got to solve for what letter? X. So what would be the left-hand side? There you go. There you go. And I just want you to get that practice in reverse order of integration. So, okay, that was a dy dx one. I don't need to do that one. I want to do one like number 4 in the practice set. All right. So what if you have this? dx dy. We'll go the other one. It's just a couple of these before you get the polar coordinates. All right. So what if you got 0 to y squared, but you're going, I don't know, 0 to, I'll get it 2. And this is x cubed plus 5 times y. All right. And you got a dx dy. And you reverse that. Well, obviously, we know the easy part. Does this change?
No.
That does not reverse at all. That stays the same surface. The order of integration will come out right there. This stuff. So this becomes dx dy, excuse me, dy dx. Alright. Now let's draw this. So I'm going to tear this thing out. These y's are x's. Alright, these are y values. Now your y. I'm going to shade from y equals 0 to y equals 2. The region bounded between are these x's or y's? Ah, that's an x equal, and that's an x equal. So I'm going to think you're the right side, and you're on the left side. These are going to be the boundary, and I'm going to shade between these two curves. That's not a curve, that's just a line. Shade between. All right. So, what does x put a y squared look like? That's one of those sideways curves like this, right? Let's draw one of those here. There you go. There's x equal to y squared. Oh, that's the right-hand side. Who's the left? X equal to 0, what is that? That's just a vertical line. Where is it? Right there. Maybe what confuses students when they see x equal to 0, maybe they accidentally think below. It's that line right here. All right. There's x equals 0. There's x equal to y squared. And you're going to shade between it from what? Y equals 0 all the way up to y equal to what? Y equals 2. Right. So where do you shade? Am I shading in here or over here? In here. When I mean shade between, that means shade between the right and the left. Shade between them, shade between them, shade between them. There you go. Man, you got it. So as long as you do problems like these two, you're fine. You can switch any way, reversing the order of integration on any problem. Is that what I'm doing that? All right, so now, these got to be x values. I don't need this. Take that out of the way. What's these x values? So I'm already stumped. I need to know what this x value was right there. What's that x value right there?
4.
Excellent. How'd you get that?
2 squared.
2 squared. So there's 4. So it looks like we're doing 0 to 4 for x, right? Okay. This is going to be a y equation. Who's on the top? And who's on the bottom? The top is this guy. Right? You go, no, that's not it. I just wrote it there. This right here was the x equals y squared, right? Here's your top. This flat line. is your top. What's the equation of that flat line? Y equals 2. And who's the bottom? It's the curve. The bottom is not 0. The bottom is that curve right there. So my top is y equals 2. The bottom is, if you solve for y, what would you get? Square root of x. Right there. Is that what I got there? There you go. That's the secret. That's the secret to reversing the order of integration. You can do one either way. I think you're good. And we'll go into polar coordinates. All right, this next section, polar coordinates. Do you recall doing polar coordinates in Calc 2? I mean, you hit it and that was it, right? Boy, is this valuable in calculus 3. Polar coordinates is so useful when your region of integration, remember I was just shading on the last few problems? When your region of integration deals with a circle or a portion of a circle. So I'll make sure to repeat that. This is a great section. When your region of integration is a circle, or just a portion of a circle, it could be a sector, or it could be a semicircle. Polar coordinates, doing double integrals in polar coordinates is way easier. I need to show you why. All right. So let's just say this is your surface. Right? Heck, I'll make it a plane. Z equals x plus y. And then we're going to find the volume underneath this plane over a disk centered at the origin of radius 2. Okay? So if we had to find this volume down and above by the surface, x plus y, but below by the xy plane, only projected over just a circle with a radius of 2 centered at the origin. We put this here, right? And let's just say we do dy dx. Look how crazy this gets here. I want you to see this. So we're getting the volume over what region did I say? Over a just a circle with a radius of 2, or you can call it a disk because we've got to shade everything inside of it, right? So I get the volume underneath this plane over that disk. I should say net volume because part of that might go underneath the x-axis. All right, so you get all that. And the radius of this is 2. We're going to see the benefit to using polar coordinates. Right now we're in y's and x's. You know what they call that? They call this Cartesian. In terms of the Cartesian plane, right? X's and y's, or rectangular coordinates. So you'll hear me refer to that. Rectangular coordinates, I'm talking about x's and y's. All right. Well, if we do this in the rectangular coordinate system, and I got to bound this, the easy part is the x's. What's the limits for x? Because this is just a circle, the radius is 2. That's easy. What's that? -2. This is the crazy part. How do you get the equation of that top semicircle? And that's the circle, everyone, centered at the origin with a radius of 2. That's x squared plus y squared equals 4. So if you haven't seen circles in a while, these are what circle equations look like when they're centered at the origin. You go, well, if they got shifted, it's a little different. Don't worry about that now. Most of these are just centered at the origin. So hey, just to go on and on and on, what's the circle with a radius of 3 centered at the origin?
9.
X squared plus y squared equals 9, right? Or a radius of 5, x squared plus y squared equals 25. You'll start seeing a lot of circles from here on out. I guess since I shaded inside, mathematically, I probably should put that then, right? Because I've shaded everything inside the disk. You know, region of integration, I'll put that. But how do you do this? How do I get that top limit? That's the top curve. I'd have to solve for the letter y, right? And this is where it gets a little weird. So when I'm going to solve for that top y right here, this y would equal, subtract the x squared and take the what? The square root of both sides, right? And what would be the bottom curve? The bottom semicircle. That would be my bottom portion. This will be my top. Oh yeah, I'll put that right here. And what's the bottom? Minus. The minus, very good. A negative square root of 4 minus x squared. That bottom semicircle would be the bottom. But I want to just you to have this in your notes just to look at and go, ugh. You follow me? Hey, now go do the math. Well, maybe it won't be too bad because you get x squared over 2 or an x all that. It still gets nasty with the what? With the radicals. I used to type this into a TI Voyage 200, everyone, and the thing would just run and run and run in like an infinite loop. It would never give me the solution because I'm typing everything in rectangular coordinates. So when your region of integration is a circle, or a portion of a circle, you definitely want to go polar coordinates. You want to use polar coordinates because it's so much easier. So the first thing is, step 1, if we're going to want to use polar coordinates for any disk, or anything projected over a disk, or a portion of a disk, oh, can I erase this? Cool, we'll get this out of the way. And we can come back to this. You and I had to derive what in the heck we're going to replace dx dy with. So if we go polar coordinates, everyone, this is called an infinitesimal polar rectangle. All right, this from here to here is the radius. So when you see my infinitesimal polar rectangle, that little tiny rectangle right there, we got to figure out what does dx dy equal. You see that tiny arc? So does anybody remember the equation for an arc? The equation for an arc of a circle, they called it S, was radius times theta. All right? But this theta in here, everyone, is infinitesimal. It's just infinitesimal as well. So I'm going to call this angle right in here, how about d theta? All right? That'll be d theta. What can I call that little side right there? This little side to the rectangle. It's a little portion of this radius r, so I can call that dr. And you got to help me out. And what can I call this little tiny arc right there? And we'll find out area of this infinitesimal polar rectangle. What would be the equation of that tiny arc?